Can start?
Yeah, C5? Да. Ну давайте.
Ну так,
Actually,
можем
it's
почему?
5 minutes. Because a lot of officers from the section is in Poltava or in Kyiv.
I told you.
They
Я говорю онлайн. Он просто говорит, пояснил, как же люди офицеры, членів, тому що ми відбували трансляцію. Я не так скажу спочатку. Так? Не може? Добре, що він не треба. Він дуже баланкою. Сказав, я ж не буду так все. Якщо дадуть, кидає все і все. Він серйозний чоловік. Нічого не казав. Я можу він? Вони так собі кажуть. Ти серйозний. Це виявляється, що мені казав, що зустрічає, все нормально. Так, вони не хотіли, щоб ми говорили, що говорили. Воно йде на сайт. YouTube.
So it's time to start our presentation. Yeah.
Okay.
Okay. So welcome.
Thank you. Can everybody hear me at the back there? Okay.
Fine.
Fine. I'm honored to be here to give this lecture. I would like to start by acknowledging that this is made possible by the distinguished lecture program of the Society of Petroleum Engineers. As you can see, the foundation for the funding for this has been provided by the SPE Foundation through its members and member societies, and a contribution from offshore Europe. The topic of my talk is basically producing liquids from shales. So this is a fairly new area. It has really been going on for the last 5 to 10 years in the United States. And that is the topic I'm going to focus on, looking at factors that control production of liquids from low permeability formations, some of which are shales. Not all of them are shales, but some of them are shales. The only thing that is common to all of these plays is low permeability or very low permeability. That means you have to use multi-staged hydraulic fracturing to be able to produce these. My name is Milind D.Deo. I am a professor and currently chair of chemical engineering at the University of Utah. I do have some cards here if you want later on to take these. We do not have petroleum engineering at the University of Utah, but we run most of the petroleum type programs through chemical engineering. We do have an online master's in petroleum engineering if you're interested. So the outline of this talk is here. So basically I'll just give a very brief background on what is happening in liquids from shales, and then go into a story that I'm going to tell you, and maybe I'll ask you some questions as I go along to figure out there is some strange behavior that we see with respect to production of liquids and gases. By the way, this lecture, even though it is somewhat structured, can be informal. You can stop me at any time and ask me questions if you'd like, okay? And then we'll go into factors that affect performance of production of these liquids from these plays and see how different it is from conventional systems. From conventional systems which are, so the big difference between conventional and unconventional systems is the low permeability. Low permeability that distinguishes them. Another thing that is going on with these plays is that we are producing what are called near critical fluids. So these are gas condensates or volatile oils, and I'll go into some of the phase behavior aspects of oils and condensates to see how that is impacting the production. And then look at geomechanical controls, because you are fracturing these after all. So that means that you have to have good geomechanical control for establishing good fractures. So we'll talk about that. And then something that we do for field-wide optimization. So there is a lot here, but as we go along, as I said, we'll try to make it as clear as possible. Okay, so here is a quick graph of production of US oil production. So US was producing, even as late as 2009, only of the order of 5 million barrels per day. By 2011, by 2013, it raised to 8 million, and by 2015, it was closing in on 10 million barrels per day. So the country basically added 5 million barrels of oil per day in about 5 years. No other country, even during the peak of oil boom, has ever done that. So this was truly a revolution. And all of these are liquids, very light crude oils that are very sweet also, very low sulfur, and basically good oils that are being produced, 45 to 50 API crude oils. And this happened on the back of these low permeability hydraulically fractured systems. But all of this happened so quickly that some of the infrastructure and controls that ought to have been in place were not in place. What I'm showing here is the amount of gas, natural gas, that is being flared per day from just one play, Bakken. Bakken is in North Dakota, and the amount of gas that is being flared, as you can see here, is almost 300 million standard cubic feet per day. Even after all the controls that they have put in place, it continues to be such a large number. Now there are more efforts to pipeline this gas and reduce the amount of flaring, but this basically was a system failure. So they are not producing gas, but they are flaring gas because a lot of the oil is light, so it's associated with dissolved gas. So the dissolved gas comes out of solution, and if you don't have pipeline for it, you have to flare it, right? So that's what is happening. But if you think about it, 300 million cubic feet per day of gas being flared, it's like 20 really good gas wells, all of them just venting or flaring. It's a lot of energy, right? Shouldn't be happening, but it's happening, okay? All of this, at least technically speaking, is simple, right, in some ways, because this is primary production from a reservoir. How many of you have taken reservoir engineering class? Reservoir engineering?
Almost everybody.
Almost everybody, right? So it's primary production. You study that in the first 3 chapters in reservoir engineering, right?
Yeah.
So this is what it is. So it's a slow overall pressure decline because of low permeability. And as soon as you go below the bubble point, you are transitioning to free gas, and that free gas competes basically for pore space and production. And so it's important for us to understand that reservoir access and surface area creation in low permeability systems also contribute to this phenomenon. So here is a graphic of a classic gas oil ratio plot for a conventional reservoir. What you see here is constant gas oil ratio in the first phase when the oil is above its bubble point. Once the oil goes below bubble point, free gas is generated, but your gas oil ratio goes down. That's because you have not hit your critical gas oil saturation yet. Until you hit critical gas saturation, your gas oil ratio is going to go down, and then it increases. See, this increase from initial gas oil ratio to this peak can be of the order of 20 times, 10 times. So if you might be starting at 500 SCF per STB of initial gas oil ratio, and you would hit a peak ratio of 20,000 SCF per STB. It's very common in conventional reservoirs. Okay, so now please keep that in mind as we look at the behavior of unconventional plays. Okay. The unconventional system, though that is for a vertical well. Vertical well draining radially, right? So vertical well that is draining radially, but the unconventional wells, and there are a lot of them. So these are all the wells in Eagle Ford, as you can see. Lots of wells, right? They're close to 10,000, I think, maybe more than that now. And they are basically drilled. They are very long. They are 1 mile long or sometimes 2 miles long, and they are fractured in multiple stages. So this is one stage, another stage, another stage, another stage. So usually you have 400 foot per stage and 50 stages, right? So that's almost 2 miles long. So it's a very long horizontal well that goes sometimes 2 sections. One section is 1 mile long. So this is basically the physical system that we are dealing with. So it's different from the conventional system where for high permeability wells where you have a vertical well draining radially. Okay. So now I'm going to show you snapshots of production from a lot of some very hot plays, meaning plays that are really good, doing really well, and plays that are not doing that great. Okay. So let's take a look at those. But before we do that, because of the system that I explained, what we want to achieve is economic and environmentally sustainable operation, right? So we want to have low low surface footprint, low amount of gas that is emitted, low amount of water usage, and all of that. And the things that are important are geologic. You have to think about completion because of horizontal wells and hydraulic fracturing. How do you operate these wells? That's an important question. And then eventually, how should a well should be spaced? Whether they should be spaced 40 acres apart, 80 acres apart, and so on. So all of these considerations are important. Okay, so let's now look at the snapshot. some of the hottest place are Eagle Ford, and Bakken. So what we see here are cumulative oil plotted against cumulative gas oil ratio. So one thing that immediately becomes not very obvious but clear is that as the amount of oil that each well is producing increases, the gas oil ratio decreases. So lower the gas oil ratio, better the well in general. Okay, there are a lot of wells that are poor wells. In fact, there are more poor wells, meaning wells that are producing less than 100,000 barrels of oil. Lots of wells that are producing less than 100,000 barrels of oil. They have very high gas oil ratios. These are very high gas oil ratios here also. But in Bakken, there are a lot of really good wells, over 100,000 barrels per 200,000 barrels per day, with gas oil ratios that are very low. That are only of the order of a couple thousand standard SCF per STP. Okay, so these are the two best places producing liquids in the United States. The next chart is where the current action is. Those Bakken and Eagle Ford have been drilled a lot. What is now being expanded is in the Permian Basin. In Permian Basin, you have Wolf Camp, and this is Wolf Creek. Actually, this is Wolf Creek. And again, you see that the gas oil ratio decreases as your cumulative production increases. One of the things is this is not normalized for time. So some of the wells are new and some of the wells are not are mature, but still the trend is what I wanted to show you, which is the gas oil ratio slowly decreases as the wells become richer and richer. And then I'm just going to go over very quickly now this Niobrara, which is in Colorado. So it's closer to where I am in Utah. And here we see not very many good wells at all. In fact, there are only a handful of wells that are over 200,000 barrels per day. And Woodford in Oklahoma, you see the same thing. So these are not that effective place for producing liquids. Then we look at some of the really recent ones. So these are brand new plays that are only like 2 years old, 3 years old. Scoop in Oklahoma and Stack in Oklahoma. Again, producing liquids, but even within 3 to 4 years, there are quite a few wells that have produced over 200,000 barrels of oil per day. So some of these newer ones, they are drilling one horizontal well, and it's not uncommon to see initial oil production of over 5,000 barrels per day. Over 5,000 barrels per day. So these are coming on, but again, you see the same trend that you have a lot of wells that are producing very high gas oil ratios. So I showed you a lot of pictures, but keep only two things in mind. The first is that for conventionals, the gas oil ratio at the peak with time is 20 times as much as the initial gas oil ratio. So you might start at 1,000, you will be at 20,000 in a few months' time. For some of the unconventional wells, these low permeability wells, we are seeing more or less the same trend. We are seeing oil wells that are very, very high. Okay, so just keep those two things in mind for now. Okay. Okay, so the methods that we use for understanding how production works is by looking at reservoir simulation. We do a lot of reservoir simulation, either by using Eclipse. In this particular case, we use CMG IMAX, the black oil simulator from CMG. Okay, for looking at some of these trends. So when we do that, this is for a typical unconventional well. So for a typical unconventional well, we see two plateaus. One, this plateau, we call it a transient plateau. So again, remember the system that I described. it is not a radial system, right? It is basically a horizontal well with a fracture, a vertical fracture, hopefully a vertical fracture. So you are essentially creating these compartments, and you are essentially draining the compartment linearly. So oil is being drained linearly like this. So this particular segment, we call it linear flow. Then it hits a plateau when it hits the boundary of the reservoir. This boundary sometimes takes, in this particular case, it took only 50 days, but it can take, depending on the permeability of the reservoir, up to 6 months or a year, something like that. It can take very long because of low permeability. Okay, but then it does not show the behavior of conventional. You see another plateau which is only about 1.5 to 2 times your initial gas oil ratio. Right? So it's very different. It's very different from the conventional behavior. So GR does not rise to very high values, and this is fundamentally different from conventionals. Right? Okay, so that was simulation, right? That was simulation, and this is field data. This is field data from a paper by Jones. This is the paper number, and well after well after well behave like this. You have as your, so you're reducing your producing bottom hole pressure like so. So why do you reduce bottom hole pressure as time increases? We do that because we have to keep the rates up here, right? Because the drawdown determines the rates. So we can start high because the initial reservoir pressure is high, but then we reduce the rates, we reduce the pressure to increase rates. So until you are above the bubble point, the gas oil ratio stays constant. Then the first plateau, linear plateau, and then boundary behavior, right? So this is, and here is some other well data, constant for a while, first plateau, kind of the second plateau, and then another peak. But we started off at around 1000 SCF per STB, and it peaks at 2500 SCF per STB, not 20,000, not 20,000. So that's a fundamentally different behavior for conventionals. And so why then do you think in the plots that I showed you of production, those are all good, that was all production data that I showed you. About 10 different places I showed you, right? Some good ones, some not good ones. I showed you Eagle Ford, Bakken, all of these. In those, the poor, some of the really poor wells, they're producing at cumulative gas oil ratios of 10,000, 20,000 SCF per STP. So any guesses as to why that could be? So remember the system that I showed you. What is happening in that system is that you have so much area, right? And you're drilling literally tens of wells in that area. You are assuming that there is no communication between these compartments. And gas is very mobile, right? If there is any communication, then the gas is going to move around and gather somewhere else. And supposing you drill into that section, then this is what happens. Your gas oil ratios right from the beginning can go to 20,000 SCF per STB, right? So this is just a hypothesis based on all of the behavior that we are seeing. If you have some really poor wells, it could be that you might be fracturing into a gas-rich zone, and that might be giving you the high GORs and very poor well performance, because a low permeability, undersaturated reservoir is not supposed to behave that way. But a lot of wells behave. In fact, out of 10 wells that are drilled, 9 behave that way, and then 1 well behaves well, like a blockbuster well. Okay. Anyway, so that's one of yeah.
What happens at the last period of production? Rates rapidly goes down, as I understand, or they do each not so rapidly at last period of production.
So the decline rates, again, it depends on well to well. In wells where you have very high gas production, the decline rates are really steep.
Yeah.
You start off at a reasonable rate, but then within a couple months, your gas oil ratios are so high that your wells become uneconomical. So the decline rates are very high. And the wells that do really well are somehow able to sustain the rate. There is some evidence, by the way, of communication between wells in other ways. What happens is you're fracturing one well, and then you go ahead and fracture a neighboring well. The water from that well ends up in this other well that you fractured previously. So that means that there can be communication between wells that are even sometimes 1 mile apart. And then if you're drilling 4, 8 wells in 1 mile section, then there is at least possibility that you're creating essentially one big pool that you're drawing from. Okay, so that could be. So this is one story. So I hope that you can take that home with you. Okay, this is one story. Anyway, so if you look at we did a lot of sensitivities, and I'm not going to show you a lot of that information, but this is just one plot that shows the impact of bubble points. As the bubble points increase as they go more towards the initial reservoir pressure. So here the initial reservoir pressure is 5500 psi. Your producing bottom hole pressure is 1000 psi. In general, you're increasing reservoir energy, and because this is primary production governed by initial gas oil ratios, your recovery also increases in an ideal sense. This is not field data, this is simulation. Okay? But then if you take all of the wells that I showed you, all of them, all 15,000 of them, and put them on one plot, this is what we did. This is what you end up with. You end up with a plot that looks like a very similar fan that I showed you. Right? It shows essentially, and this behavior we can understand by assigning basically a compartment and saying that a finite reservoir that is producing liquid would produce, we would essentially max out here, but then because of the presence of gas, you have this additional increase in recovery rate. These are what we call adjusted recovery factors, which are, the definition is given here, where you have the recovery factor. This recovery factor is a common definition for dimensionless analysis. This adjusted recovery factor also has drawdown in it. And we basically can show that your entire all of the wells can be normalized by putting them on a plot like this to understand how the reservoir mechanics are working. And if you do that, we can then start looking at the various parameters that can influence production. So in this is kind of a busy table, but you have two types of parameters here. You have operational parameters and reservoir parameters. By reservoir parameters, I mean something like permeability or viscosity or compressibility and so on. And then operational parameters are number of fractures which you can control to a certain extent. You can control operational pressure, right? Bottom hole pressure you can control. So those are and fracture spacing you can control. So basically what the plot that I showed you helps us understand is that in the earlier portion of the system, so in this portion where all of the wells are in linear flow, in this portion of the system, we have pressure drawdown, which is both a reservoir parameter and an operational parameter. Larger is better. Number of fractures, of course, the larger the number of fractures, the better. And fracture spacing, smaller the better, and so on. So we can look at those type of influences. And obviously oil viscosity, the lower the oil viscosity, the better, because as more gas is dissolving in the system, the oil viscosity is lower, and that helps you increase your production. And so we can do the same type of analysis for boundary flow as well. One of the things that you do see here is that matrix permeability, which is like the number 2 factor here, goes down in importance as you switch from transient flow to boundary flow. So some of those things become clear in that sense. We also take a lot of these reservoir simulations, make what we call surrogate models or response surfaces that represent those reservoir simulations. So we may have, say, 1,000 reservoir simulations, and then we put them into some kind of an analytical function, a fitted function, then which we can run Monte Carlo simulations on, and we use those Monte Carlo simulations to figure out what parameters are of importance. And when we do that, we end up with a fairly detailed table like this. So what we see here is the importance again of those similar parameters that I showed you. We have 1 year recovery, 10-year recovery, 20-year recovery, and if you assign an economic rate of 5 barrels per day per fracture. So supposing you had 100 fractures in the system, 400 barrels per day would be your economic rate, minimum rate that would sustain. And then look at the importance of different parameters. It turns out that out of the 8 parameters that are listed here, 6 parameters are geologic, meaning things such as matrix permeability, initial pressure, compressibility, gas relative permeability exponent, so things like that which you cannot have, which you don't have much control over. The 2 parameters that you do have control over are hydraulic fracture spacing and producing bottom on pressure. So these parameters turn out to be the operational parameters that are important in recovering more of the oil from these type of systems. And again, I'm going to show you the importance of those 2 things that we can control. So again, from your reservoir engineering texts, you can see there is a plot here from a very old paper, Levin and Pratt's, 1960, a very classic paper. See, at that time, again, those of you who are students of petroleum engineering, computers were just coming up. In fact, IBM developed some of the first computers for Exxon Mobil. At that time, there was not, it was just Exxon. For Exxon, they developed those computers, and Levin and Pratt used those computers to do reservoir simulation, and they developed this plot. They developed a plot as a function of permeability, as a function of recovery, and showed that the permeability can go up to about 12% or something. The recovery can go up to 8% in this case when reservoir permeability increases. This is 1 millidarcy, 10 millidarcy. This is millidarcy. And here we are looking at nanodarcy. Nanodarcy permeability plotted very similarly on a log-log, the semi-log plot. So this is logarithm of permeability. So this is in nanodarcy though. And as you can see here, so the thing that becomes clear is that when you have really, really low permeability, let's say 100 nanodarcy, if you are at 150 foot fracture spacing, you are at 150 foot fracture spacing, you are going to have recovery only of about less than 5%. But if you reduce that fracture spacing to 20 foot, then your recovery can quadruple, can increase 4 times. So the effect of fracture spacing when the permeability is low is very, very clear. When you have higher permeability, then it's not that clear, right? Everything is bunched up. So you don't gain a lot by reducing your fracture spacing. And that dependence is almost exponential. So as your permeability increases of the reservoir, you don't gain very much by going to shorter and shorter spacing. So you can actually go to long. By going to shorter and shorter spacing, what do you lose? You have to pay a lot more for the fracturing job, right? So it's an economic question. How short can you get?
How was the lowest measure of permeability? I mean, economical limit. Lowest measure. Nanodarcy,
About 500 nanodarcy.
Five.
500, 0.5 microdarcy.
Five.
So the economic limit usually is somewhere here. Okay. So that was for black oil reservoirs. Because all of that analysis was for black oil reservoirs. So in some ways, black oil reservoir is an arbitrary designation, right? It's a convenient way for us to represent the oil. But the oil is not a black oil. It really consists of tens of thousands of components. In fact, there is a mass spec now in Florida, very high resolution mass spec, that recently was able to identify 30,000 compounds in Arabian light crude. 30,000 compounds, right? So oil is a very complex multi-component mixture, and that multi-component mixture, depending on how light it is or how heavy it is, can be classified as a condensate or can be classified as a volatile oil. Okay. Eagle Ford is a classic textbook example of production of these various types of oils. So in fact, you can see that this is Eagle Ford. This is kind of a cartoon of Eagle Ford. Okay, it is very long. It is 50. This is 50 mile scale. So this is about 100 miles this way and 400 miles that way. So it's a very long plane. Okay. And if you go from northwest to southeast, you're going to go from oil to a condensate to a dry gas. All three types of fluids are produced within 10 miles sometimes. In fact, there are a lot of companies that are producing a fluid and they don't know whether it's an oil or a condensate a lot of times. Okay? Because that's how these fluids are. And Eagle Ford is overpressured and is very hot also, meaning it has temperatures very close to 300 Fahrenheit. And as a result of that, it can be in the condensate window. So the type of fluids that are produced in Eagle Ford, I just gave you 5 types of fluids that are being produced in Eagle Ford. Again, I don't know, you're in a reservoir engineering class, you know how things are classified, but a C7 plus of the order of about 9 to 12% is in the condensate window. Okay, above that you go into oil, below that you go into wet gas. Okay, so that's the way it works. And if you
we use C5 plus condensate.
Not C7 plus, but C5.
C5 plus.
you do C5 plus.
Yes.
Okay. Okay, yeah, there could be different definitions. Anyway, it's lumping of hydrocarbons of different types. So here is the phase diagram of those 5 fluids that I showed you. So as the fluid becomes heavier and heavier, the phase diagram gets bigger and bigger. Okay, and these are the critical points here: 1, 2, 3, 4, 5. 5 critical points. So where is the condensate window? Which part of the critical point is on which part of the critical point does the condensate lie? So for this, let's say this pink fluid, right? So here is this particular temperature is the highest temperature on the phase diagram is called the cricondentum. So any temperature between critical point and cricondentum gives you a condensate window. That's because supposing you are here somewhere in this temperature range, right? And you're basically depressurizing, meaning you're coming down. You're coming down in pressure. And this is the dew point curve, right? The critical point, bubble point curve, dew point curve. So when you reduce your temperature, when you reduce your pressure, what are you going to hit? You're going to hit a dew point. So it's counterintuitive, right? You think that as you reduce your pressure, you're going to get gas, but instead you get a liquid. So that's why they are called retrograde condensates. Retrograde because they behave in a way in which they are not expected to behave, these fluids. And what these phase diagrams show is that the type of fluids that you see in Eagle Ford are very amenable to producing condensates at different temperatures, at temperatures ranging from 250 to 300. Any of these temperatures can produce condensates. Okay. So with these type of liquids, we did again reservoir simulation. So in this case, reservoir simulation has to be done using compositional simulation. You can do Eclipse 300, or you can do GEM. How many of you have used GEM? CMG's GEM.
No, we don't have.
You don't have CMG. That's actually a good program. Anyway, so when you do that, again, there is a lot of information here, and I'm going to walk you through this pretty quickly. In condensates by American terms are described as liquid to gas ratios, right? So it's reverse than gas oil ratios. So a condensate that is 200 to 300 barrels per million standard cubic feet is a rich condensate, usually. Usually, if you produce 200 barrels for every million standard cubic feet of gas you're producing, it's a rich condensate. If you're producing 40 barrels for every million standard cubic feet, it's a lean condensate or a poor condensate. So I'm showing you two plots, one for a lean condensate and one for a rich condensate. Okay? Rich condensate. And both of these are for the end member permeability, really low permeability. So 100 nanodarcy. So your professor asked me, what is the minimum permeability you could have for an economic oil well? There is no good answer for that, but in general terms, the answer is about 500 nanodarcy. But for gas, you can get away with lower permeability.
Low.
Yeah, you can with gas you can go to 100 nanodarcy and you can be okay, right? So these are initially gas, but they're producing liquids because they're condensates. And one thing that I want to show you here is this is a recovery plot when you hold the bottom hole pressure to 3000 psi, this pink one or red one, and this is the recovery when the bottom hole pressure is 1000 psi. So you basically double your recovery by essentially holding back pressure on your system, right? You are essentially doubling your recovery from about 12% to 24% by just doing that. And then there are other things that we can do. We can actually gradually, because you cannot hold back pressure for so long, you have to gradually reduce your back pressure, right? So here is stepwise reduction of back pressure, or here there is a very quick reduction of back pressure from 3000 to 5000, 3000 to 1000 psi reduction. And I show a couple of other recoveries to show those cases, and they are not that different. So, for example, this 2-year reduction basically gets you just a little bit of lower recovery, and that's 2-month reduction or 3-month reduction gets you recovery that looks more like your original 1000 psi recovery. So basically, for these near critical fluids, as we call them, it is better to hold whatever back pressure you can hold on the system, because it is better to not drop the condensates off in the well so as not to lose them or block them. But for a rich fluid, it doesn't make a big difference. Rich fluid is a little more forgiving in terms of how much back pressure you can hold on the system. So anyway, so this is another take-home lesson where we see that holding back pressure actually helps you in some ways. And some of the producers are already doing that. This is a 2 years ago, this came out of a bulletin that showed that oil drillers are choking wells, meaning they are holding back pressure on the wells to make sure that they kind of keep the liquid rates up. And this kind of has gone into some practice, at least for the condensate wells. This is a Canadian play that people are talking about, but again, that's something that people are practicing. Okay. We have understood that fractures are being used for generating surface area in this case, right? So the fractures have to be very effective. And we look at fracture morphologies a lot, and we do that by using what's called a discrete element model. So we develop these models. We work with a national lab, Idaho National Lab. One of my PhD students helped develop this particular model that I'm showing you. There are two grids here. One is a mechanical system grid that is described by these particles. And you can have particles of various sizes to assign heterogeneity to the system. And then you have a flow network that shows how the fluids move into the system. There are not that many simulators that can do this type of simulation where you have mechanical representation and a fluid representation at the same time. Okay, and using that we can actually model these multiple staged horizontal wells. I'll show you a couple of examples here. One example. So I'm showing you two plots here. The first one where the stress between the maximum and the minimum, there is a contrast of 0.5. So this is a plan view, and the stress is high in this direction and low in this direction. So obviously you have fracture propagation in direction parallel to the stress, and you see how everybody can see this. It's these are more by what we call bi-wing fractures, whereas this low stress contrast produces fractures that are somewhat crossing over and intersecting and so on.
So
right?
high stress is much more better.
High stress is better. High stress contrast. High stress contrast is better. And this we can quantify, which is, I mean, it is somewhat intuitive, and you can do that using Gopher or something. But in Gopher, you can only do planar fractures. So these are non-planar kind of meandering fractures that honor the heterogeneity of your rock. Okay. So this is basically the same thing that describes why that happens. Fractures propagate parallel to the maximum. When the stress is lower, then they can start intersecting and create a more complex fracture network. So we used that kind of a program to represent a full-scale heterogeneity in a system in Eagle Ford. This is a 24-layer model. It has about 300,000 particles. And this was published in this paper, Geotech 2170875. It's an SPE paper. You can find it on OnePetro. You probably have subscription to OnePetro. And see, the company asked us to figure out, this was somewhat exciting because they wanted us to figure out if it's good to place the well in the top of the Eagle Ford or bottom of the Eagle Ford. Okay? So I'm going to show you a simulation only for the bottom of the Eagle Ford. So this simulation, by the way, takes a couple of days to run because it's a pretty involved simulation and full heterogeneities in the system. So each of these layers has its own mechanical properties. Each of the layers has its own permeability. and each of the layers has its own porosity. So it's a complex system, and what you are seeing is pressure. So this is net pressure in the system, and now you can start seeing fluid leak off along the edges of the layers, and each of these are different. So as it comes to a high permeability system, it loses the fluid in there and loses the energy. And as a result of that, the fracture can either turn over or basically die. Right? So this basically captures all of this. So this type of a capability basically lets you understand how to effectively create the type of fractures you want to create. And you can then look at the effect of, this is effect of natural fractures. So again, so now we have, you're hydraulically fracturing a natural fracture environment. So what we are seeing is a high viscosity fluid that basically goes through the fractures more or less, right? It's not opening up fractures, whereas a lower viscosity fluid is reactivating the fractures. It reactivates this fracture, that fracture, and creates a more dendritic kind of a complex fracture network, whereas this fracture is a straighter fracture. Okay. So we can use these type of things to create some set of rules. I'm not putting all the rules down, but just basically shorter fractures with large apertures can be created by using high viscosity fluids. And depending on your geologic environment, you can then decide what is the best way for your well, what type of production strategy you want to have. Biling fractures in high permeability formations and clear stress contrast. Again, you have high viscosity, higher rate, and so on. So the stress shadowing is where you would have two fractures growing, and then because they are growing, it is creating higher stress in the interior region. And so anything that's in the intermediate region is going to have difficulty growing. So that's called the stress shadow effect. But you can overcome that by spacing the fractures a little bit. So this is the geomechanical effect that can constrain you in how short you can go in terms of fracture spacing. So you may go to 20, you may want to try to go to 20-foot fracture spacing, but if you try to do that, you might have the stress shadowing effect. So you can, but you can understand that by performing simulations of this kind. All right, then finally we can start taking all that information, the fracture information, different types of, so this is well number 1 that has various fractures, well number 2 that has various fractures. Then you may have multiple wells in the system. So we basically have created a workflow to take these complex fractures, multiple wells into one simplified system, and we showed this in a Bakken network, in a Bakken system where you had 3 wells, well 1, well 2, well 3. This is all in one section, 3 wells, and they were highly heterogeneous, as you can see. The permeability field varying from about I think 0.7 millidarcy to 0.29 millidarcy or something. Okay, so it's a layered model with a highly heterogeneous system. So you can use that information, and we were able to use the type of morphology of the fractures I showed you and well representation to match the oil rates reasonably well. So these are, you asked about decline rates, so you can now see the decline rates here, starting around 5,000 barrels per day, and then in about 2-3 years, it gets down to 100 barrels per day for one of the wells, or more or less all 3 wells behave the same way. We were able to match this using that workflow that I showed you, and you can take that type of information and put it into some kind of an economic analysis to see how many wells can you have for a given fracture spacing. So obviously, if you have 8 wells, you can have your fracture spacing has to be larger, and as you go to smaller number of wells, 4 wells, you can get away with shorter well spacing. So your internal rate of return then determines how many wells and what kind of fracture spacing you have. So you can use that type of workflow to create an economic model for producing these type of systems. So basically then, in conclusion, we can, I gave you that importance of gas-oil ratio. The gas-oil signatures for low permeability, hydraulically fractured reservoirs are different from conventions and provide an understanding of production. Matrix permeability and fracture spacing are two of the most important factors that determine fluid recoveries. Improving recoveries for condensates, these near critical fluids. I mean, you have to have an integrated understanding of reservoir and operational parameters. Holding higher producing bottom hole pressures leads to higher recoveries, often to higher liquid rates for near critical fluids. It's possible to represent most liquid data in North America on that single curve that I showed you. And then geomechanical models may be used to guide operation of desired fracture morphology. And then finally, you can integrate all of this into a framework that will give you how many wells you can have for a given fracture spacing and vice versa. So basically that, I think, concludes my talk. Most of this work was done by my PhD students and a couple of colleagues here. This person, Idaho National Lab, John McLennan is a colleague who is a geomechanics expert. Dr. Raymond Levy, the director of Energy and Geoscience Institute, which is a upstream industry consortium at the University of Utah. That concludes my talk. Again, I would like to thank the SPE's Distinguished Lecture Program for making this possible. And I'm very happy to come to your very nice city. Thank you. Happy to answer questions.
Can I have one?
Yeah.
You told that you use the CMG for your simulation. Why? Why it's better rather than Eclipse compositional or black oil model? Depends from your tasks.
Is it on record or off record?
It's still on. You want me make it off?
I think they are completely equivalent. CMG, especially for students, I think a little bit easier to use. But Eclipse is also integrated with more geologic packages. Of course, now there are rescue formats that you can bring Eclipse into CMG or CMG into Eclipse. That's possible. But just if you start off with something, the learning curve is a little less steep for GEM, particularly for compositional simulation. And it's very robust. It's very robust for meaning it's very forgiving in some ways. So, for condensates.
What software was used to perform the CFD? The CFD simulation?
Which simulations?
What software was used to perform the simulations?
So I showed various packages. The black oil simulations, the last ones that I showed were done in Eclipse. The one before that were done in Computer Modeling Group, CMG. So The black oil simulator there is called IMEX, and the compositional simulator is called GEM, GEM. So GEM is equivalent to Eclipse 300. It's a compositional simulator. And for condensate, you must use a compositional simulator.
Of course. Phase diagram. You explained everything. And I'd like to ask you about dropped condensate. How we can produce more condensate? What do you recommend? What's like in USA technology, maybe better methods to enhance dropped condensate recovery?
I mean, of course, one of the methods was that we can manage the back oil, the pressure and flow rates more effectively. But other than that, there are some half and puff type methods that people are looking at, but nothing has been proven in shales at least for condensates. So this is still primary production out of condensates. If you drop condensates and if it is below your mobility, condensate mobility, then there is not much you can do.
Like maybe nitrogen injection,
Right.
or gas injection, something like that.
It's all possible for conventionals. For unconventional,
No possible.
right now.
That's the main
Not
reason, yeah.
Right.
It's the main difference between.
Is injection one of the concerns? Short circuiting and so on for nitrogen.
In one slide, you show the influence of different parameters on reservoir performance, yes, and the fracture parameters have them more influence, yes, rather than even the bottom hole pressure. Could you please explain it more?
In that case, those were all still important parameters. They were just ranked in the order of importance. Yeah, as you could see, some of the problems with the reservoir, meaning very low permeability, in the beginning has to be overcome with because you cannot put that kind of a drawdown on your reservoir almost immediately because the fractures end up closing, and because of that you fracture spacing allows you the most flexibility in recovering more. That's why they ended up at the top compared to the bottom hole pressure. But bottom hole pressure is almost as important. I mean, if you can tolerate a higher drawdown, but with higher drawdown you are going to produce at a higher gas oil ratio. I mean, your recoveries are higher because liquid rates are higher, but you might end up producing so much more gas that you have to figure out how to manage that gas. That's another reason why the importance was slightly lower.
What's the optimal length of horizontal well? I mean, horizontal path, and how many fractures or the distance between every fracture in this path?
Yeah, unfortunately, there is no optimal length. The longer you go, the better in this particular case.
The longer is the better.
Right.
Because low permeability or
Because of low permeability, right. And unfortunately, some of the more complex reservoir characteristics, such as faulting and compartmentalization, are not modeled here. They have to be case specific. If that comes, then obviously your well length is determined by more of the overall geology rather than the stuff that I showed you. The stuff that I showed you was more immediate petrophysics of the reservoir, things such as porosity, permeability, compressibility, and all that. Whereas if you're going really long, then you have to really think about what's happening to the structure of the system, what kind of fractures you're dealing with, faults. So you have to think about those type of things. So those might limit the length of your
In you said that if we want to get better production rates, we should have our fracture lines parallel. Yeah, maybe I missed the moment when you explained how to do that. So can you repeat how to manage it, how to have our fracture lines parallel so they don't touch each other?
For the most part, you cannot control it. It's controlled by the stress regime. So if you have higher contrast between your maximum and the minimum stress, you're more likely to create the parallel fractures that you want, the long parallel fractures that you want to create a larger surface area. But in case you have natural fractures, or if you have low stress contrast, you can overcome that slightly by increasing the viscosity of your fluid or by increasing your rate. So those are the two knobs that you can turn but then you will ask how high can you go and how high of a rate. That is case dependent, and that depends on your specific parameters of your mechanical properties and other fluid properties in the system. But in general, you can slightly overcome this effect that I mentioned of stress shadowing and all of that by increasing the rate and viscosity of the fluid. And people are already doing that. So instead of using slick water, they use a specific polymer in the system, or again, they are called mega fracturing, so the rates are very, very high. And also, another thing that I didn't mention, okay, just on this case is propant. So in our simulator right now, there is no propant transport integrated in it, and that has a big impact. How much propant you can carry, and the more viscous the fluid, the better capacity it has of carrying the propant.
What about minimum distance between fractures? Maybe based on the field data.
So again, based on what I showed, obviously I showed you the relationship between permeability and fracture spacing. So lower the permeability, lower has to be the fracture spacing to get reasonable recoveries. But there is an economic optimum there, and an optimum that is determined by geomechanics. So the closer you go, you're going to get these crossovers and interference. So that we think for the type of system that we looked at, 100 nanodarcy and very typical geomechanical properties of the order of 60 feet, 50 to 60 feet. If you go lower than that, then you are going to have difficulties propagating all the fractures.
You gave a very good example, very interesting gas, condensate, wet gas field. Yeah? And mostly we have a difference with the depth. It's in the first position, it's will be oil, gas, and gas
Right,
condensate.
that's true.
And with depth, what's the difference in that oil in that field?
As you go deeper, you get gassier, so you get lighter. But it's not completely correlated to depth. It is somewhat correlated to depth, but not completely. So, in general, though, you're right. As we come from the oil window, the condensate window to gas window, you're going deeper and hotter. You're going deeper and hotter. It's a good textbook example. So, those of you who are studying again reservoir stuff, you might sometimes think that the fluid stuff that we study is not that important and all that. Here's a textbook example of why fluids are so very important. You absolutely must know the type of fluid you are producing before you can design a production operation. Very important. Any questions online?
Yeah. No questions online.
Шеф, письмає питання? Does anyone have questions?
Well, as I said, you have a very nice city with the mountains and everything. Salt Lake City is very similar. We have mountains about 20 minutes from where we are, 6 ski resorts in distance of 20 minutes. I was going to show you some pictures, but I guess we ran out of time. But I can show you some. It's a very pretty state, 9 national parks and all that. So if you come to the US, do come to Salt Lake and visit. Okay, thank you very much.
Thank you very much.
I have some business cards if you want.
Take a picture.
Хто хоче фотографію, чекайте на виході з університету. Ну, а де тут так? Next, you're in our
Я думаю, вже можна зупинятися.
Хто хоче фотографуватись на виході з університету? Зараз станемо, скільки